You might think a wind turbine's survival on a freezing mountain ridge comes down to just having incredibly thick steel.
Right, yeah, that is a super common assumption, like just build it bigger, make it heavier.
Exactly. But if you look closely at a technical glossary on precision transmission setup, which is exactly what we are unpacking today on the deep dives, you realize the real secret isn't bulk.
No, not at all. It is perfectly engineered internal geometry.
Right. Our mission today isn't to give you a vocabulary lesson. We're going to translate dense mechanical engineering terminology into the fascinating realities of how extreme machinery actually survives. So, okay, let's unpack this, starting right at the heart of the gear system with something called a full complement bearing.
Yeah, that is a foundational component for sure.
The best way I can picture this is, well, imagine a crowded subway car at rush hour. Normally, you have seats taking up space.
Right, and in engineering, the structure separating the rolling elements is called the cage.
Exactly, the cage. So a full complement bearing essentially rips all those seats out of the train car. You do that so you can cram in as many passengers or, rollers as possible.
Spot on. By removing that cage, engineers pack the internal space with load-bearing rollers. The engineering notes explicitly state, and I will quote this directly, "We selected a full complement bearing for the planet gears to maximize torque capacity within the limited internal space."
Oh, wow. So you're trading the high-speed capability that a cage provides for pure, raw torque in a tiny footprint. Wait, for those picturing this, when the text says planet gears, it is literally like a solar system, right?
Yeah, that is a perfect way to visualize it. You have a sun gear sitting in the middle, and these planet gears orbit around it. And what keeps this hyperdense powerhouse functioning is a brilliant mechanism called self-centering.
Wait, self-centering, how does that actually work?
Well, in these precision systems, that central sun gear actually floats. Because it isn't rigidly fixed in place, it automatically finds its own center under the opposing pushing forces of the surrounding planet gears.
Oh, I see. So it naturally compensates for minor mounting errors.
Exactly. It ensures an even load distribution across all four orbiting gears.
Okay, so removing that cage creates immense torque, but cramming all that metal together under equalized pressure has to create massive heat and friction. How does the system keep from, melting itself down?
That is where fluid dynamics come in. And what's fascinating here is how we measure a fluid's ability to survive extreme temperatures using the viscosity index, or IS.
Viscous.
Yeah. A high viscosity index means the oil's thickness remains incredibly stable even when the temperature swings drastically.
So for high-altitude applications, you require a synthetic oil with a high 6 to ensure a smooth startup. Otherwise, your oil turns into thick sludge the moment it freezes, right?
Precisely. You need that perfectly engineered synthetic oil keeping the friction down.
But looking at the radial shaft seal, which is, it's this spring-loaded lip protecting the rotating shaft, I have a genuine question. Well, the maintenance schedule demands an inspection exactly every 2,000 hours. That feels incredibly rigid for an industrial setting. Why can't a technician just wait until the machine sounds sluggish or starts running hot?
I mean, because waiting for a noise means the damage is already done. That radial shaft seal is the primary wear part protecting the entire system from the outside world.
Oh, so if it fails, it's game over.
Exactly. The strict 2,000-hour inspection rule is there to, quoting the glossary directly, prevent lubricant loss and ingress of environmental contaminants.
Ah, I see. That spring-loaded lip is constantly rubbing against a spinning metal shaft.
Right, it will inevitably wear down, and if it fails, your high-V oil leaks out and destructive grit gets in.
Okay, so we have this highly specialized oil locked safely behind a 2,000-hour seal. But whether that oil actually reaches the gears it is supposed to protect seems to depend entirely on one final human element.
Yes, how the machine is oriented when it is bolted to the floor.
Exactly. The critical term here is mounting orientation. Like, are you installing this equipment horizontal, vertical up, or vertical down?
Yeah, and the manufacturer refuses to even build the gearbox until you tell them exactly which way it is going to face on the factory floor.
Wait, really? Why are they so obsessed with the angle?
Because orientation dictates the internal fluid dynamics. It determines the exact position of the breather and the oil drain plugs.
Oh, wow. So if you mount a gearbox vertically that was designed for horizontal use, your oil pool is in the completely wrong place.
Exactly. The gears might run dry, and the heat dissipation will fail completely. The installation angle changes everything about how the machine regulates its own temperature.
That is incredible. Mastering this technical vocabulary really isn't about, just memorizing words.
No, it is about understanding the fundamental blueprint for a machine's survival.
Right. From tearing the seats out of the subway car for more internal torque to the exact angle it sits on the factory floor.
It is all connected. Every term represents a physical reality that keeps the system alive.
It makes you wonder, if a seemingly minor detail like a machine's mounting angle fundamentally changes its internal fluid dynamics and its ability to survive, what systems in your own daily life or work are underperforming simply because they are, well, installed from the wrong perspective?